Good afternoon and welcome to this webinar provided by oh, Good afternoon and welcome to this webinar provided by bobwillis.co.uk. My name is Bob Willis and I'll be presenting today's webinar. Before we start talking about process defects and process defects solved, I'd first like to introduce you to the control panel, which you have on your screen at this moment in time. The control panel allows you to do a number of things during the presentation. First of all, you can close and open the control panel by clicking on the orange button. This prevents it obscuring your view of the slides during the presentation. If you want to go full screen on your projection facility or on your PC monitor screen or possibly on your cell phone, then click this button. If you've got any questions at any time during the webinar, just type them directly into the control panel as indicated here by the red arrow. Now, the questions we'll answer at the end of the webinar, but please type them at any time during the webinar and I'll pick them up and answer them, if I can, at the end of the webinar this afternoon. Now, if you have any technical problems, please use one of the telephone numbers provided on your registration and reminder emails. You'll also need your webinar ID number and access code, which was included on your email. It's not possible for the presenter to assist you during a live presentation. I can't multitask, that's the problem. Please remember, the internet is still under considerable strain at the moment, so if there is a local speed problem, if there is perhaps a problem in your country or even in your own facility, if everybody is taking a break and looking at things on YouTube, just bear with us. It may just be a local thing. At the end of the presentation, we have a couple of survey questions on the webinar and its content. Please just take a couple of moments to complete that. It gives us feedback on the webinar, the content, how I can improve my presentation, or things I can include in the future. We will be sending you a copy of the presentation material shortly after the webinar, and you should receive that within a couple of hours of the webinar, but please check in your junk folder just in case it's sneaked in there and not gone directly into your inbox. It does happen occasionally, so please check that out. A little bit about my background first of all. I've been involved in mechanical engineering all of my working life. I've worked in printed circuit board manufacture, environmental test, testing products, environmental testing, failure analysis. Obviously, I've worked in assembly, otherwise I wouldn't be talking to you. And I've worked in contract manufacturing. Over the last 30 years, I've had the pleasure of running training courses for a variety of different organizations worldwide. And of course, in the last sort of 6 or 7 years, I've been doing a lot of the training courses that I offer online, specifically for companies or groups of companies in different parts of the world. At least I can sort of stay at home. I don't have to travel too much, which is the non-fun bit of the exercise. So what we're going to be talking about is process defects. I'm going to get you to do a little bit of work this afternoon, but some of you have already done a little bit of work in kindly sending in some examples of process issues. Now, this is completely anonymous, so anything that I talk about won't be related to a company at all, but people have been kind enough to send in some examples, and it's more immediate, it's more interesting to solve, hopefully, problems for customers. But over the years, I've looked at a variety of different processes, materials, etc. for customers, and hopefully I've tried to solve problems in a practical, pragmatic way. Hopefully I've succeeded in some instances. So basically, over the last sort of 6 or 7 years, a lot of my work has been done online, and although I miss the hands-on immediacy of this sort of thing, it still works pretty well. I'm very pleased. So fundamentally, what happens if I'm doing presentations, just like I'm doing now, for 1, 2, or 100 people, I sit at my desk, I give a presentation, and I answer questions. So I've done this for companies and done it regularly for companies to train groups of staff in different disciplines. And simply, this is the pattern. Information I get, answers and solutions I give. So that's how it works. And these are just some of the people in audiences all the way around the world. So that's how I've been doing a lot of stuff in recent years, and more than happy to continue to do that for individual companies. Other things that I've done is also I help create the Defect Database, and this is something that has run and put together with NPL. And this is basically photographs of problems or process issues, and we've highlighted those and give some sort of indication of why they may occur. This was part of our another project that we were doing at NPL, and also part of the PPM project, monitoring yields, that I did a few years back. In addition, I publish my Defect of the Month videos, and there's over 70 of these on my YouTube channel. So again, if you're looking for a solution to a defect, that might be there. Or alternatively, it might be new ones that I'm producing. And I'm hoping to produce another range of these and hopefully supported by some suppliers. So if you want to get involved in those, then just contact me separately offline. I've also had the pleasure of producing some documentation, books, defect guides, publications. And again, if you look at these all are available to download, or most of them are available to download somewhere on the internet. So if you do a search for any of the Bob Willis defect guides or Bob Willis book on POP, package on package, pin and hole intrusive reflow, cleaning and contamination defect guide, sort of all of these are available somewhere on the internet. So just do a search for those. Some of them might be available also from my own website. So that's sort of my contributing to the knowledge base that exists within the industry. Now, I'm going to be asking you a few questions, and we're going to be doing a few surveys during our time together. And I just listed here the ones that we're going to be doing. And I'm going to give you the results of these later on when I send out information to you. But it's important to understand, out of close to or just over 100 people that are on the webinar, where are we starting from? What are we trying to achieve? What standards do we work to, or what criteria do we work to? So I've got a number of survey questions that I'll be answering you. It's very simple. All you need to do is click the right answer, or click the answer that's most appropriate to you, your company, or your organization. So again, that will give us a graphical representation of what 100 engineers said on a particular subject. So it's a little bit of homework for you as we go through the webinar this afternoon. Now, so let's pick up on the first process defect. So just to set the scene, a week ago, I launched this webinar title, and I asked people to contribute defects that we're currently having or have problems with or have not been able to overcome. And I said, just tell me what it is, show me some photographs, and I'll try and make some suggestions. So this is one of the first ones that I got, which is all about voiding, which you probably guessed from the photographs. So a customer was assembling this bottom termination device, and the center image illustrates to you the footprint on the PCB the company is assembling. And if you then look over to the right-hand side, he's illustrated to me the voids and void contact. And what he's trying to do is improve the amount of voids on his process or his package. He is not necessarily outside of any criteria that's generally discussed in the industry, i.e. maximum of 25% voiding by surface area, but he and his customer would like to improve it. So if we look at this first example, inevitably, and he hasn't told me about the stencil design or any of those nice things, but I assume that he's using standard design rules by breaking up the footprint. But the first thing that you see is vias. Now, these vias are filled and plated vias. So he's filled them, he's plated them, and there are other examples on the board. Now, but still, one of the reasons why we can get voids is outgassing from vias, and that can still happen even though they're filled and plugged. So I'm a great fan of trying to eliminate paste getting into the via in the first place. And if you can do that by clever stencil design, but still giving you the right volume of solder, then that's a benefit. And one of the ways I do that is I put resist donuts, resist circles around the vias. And then you print around the area, and then the paste during reflow does not go into, and it reduces the possibility of voids forming. So that's one thing that can be done. But fundamentally, if the board is going to outgas, or anywhere around the board is going to outgas, that can particularly give you this problem. There is a limit to what you can do with any solder paste technology and profiling. And if you've experimented with, as I understand the customer has, experimented with different profiles, different pastes, etc., then it's not the norm that is causing the problem. So profiling paste, by improving that, yes, you can improve void formation, but we're trying to get to the nitty-gritty. So things that can affect, first of all, outgassing from the termination itself. So if you've got a plated part, and if it's tin, as most parts are, sometimes you can get organics outgassing from the plated part itself, so the actual termination on the component. And I've demonstrated this on tin-plated components in the past. So simple experiment is to just look at what's actually happening on the part if you reflow some solder on the termination. Just see if you can see any bubbling or gassing, and do that under a microscope, and that will allow you to understand potentially the problem. Now, just to highlight a test that I use quite often, it's all covered on my YouTube channel, and this is the oil test. If you've got vias, capped vias, plated vias, filled vias, you can always use high temperature oil and do a simulation, i.e. you're heating up the pad and seeing whether any volatile material is coming out of the via or out of the via plating. So you can see this on my YouTube channel. It's just high temperature clear oil, and you're just heating up the pad and seeing what happens. In this example, I was doing this on a production site. Now, these are a package. The via holes have been filled with an epoxy in PCB fab. These are not plated over, so you can still see them gassing, but you could probably get the same phenomena take place even if they were plated over. So potentially there's where gassing could occur. And this is 9 times out of 10 moisture in the printed circuit board. So reducing moisture content through experiments with different baking times and regimes and temperatures may be a way of reducing the problem. But inevitably, all boards have some level of moisture in. Another thing with bottom termination components is that what we can get is gassing from the laminate surface around the pads, or sometimes from underneath the solder mask. So this is just another experiment with another part, and what you're looking at here, we're actually showing the gassing through the oil again. So I've got oil, I'm heating the board up on a rework system, and you can actually see the gassing taking place. So this isn't actually on the pad, but it's around the pad surface. Now, whether or not that would impact the amount of voids that you might see, I can't guarantee that. But again, that's just another experiment. So in the situation that the company showed me, I would certainly look at what we can do about the vias, check outgassing for the vias. If we can prevent solder paste sealing the gap between the via and the package, if we can eliminate the board creating the outgassing within the solder volume, which it clearly would from the vias, that's another thing to look at. And also compare the amount of voiding with pads that have vias in and pads that don't have vias in. So that would be, what I would do if I was looking at this particular problem again. Process defect number 2. Now, a company has been looking at failures, intermittent failures of joints, but in this particular case, this is actually a BGA solder joint to a pad and the track coming into it. So you've got a track underneath the solder resist coming into it, and it's cracking. Now, this type of phenomena is quite often seen during vibration or drop testing. So if you're doing vibration testing or drop testing, particularly on thinner laminate materials, so if you're on a 1 millimeter laminate, yes, it's more likely than on a 1.6. But if you're even on a 1.6 thick laminate material, you could still get this phenomena. Now remember that with BGAs and lead-free BGAs and the solder we use today, it's harder than tin lead. So all the energy during flexure will be focused on the weakest point, and quite often that's at the edge of the pads where that is being flexed, either by vibration or drop. It potentially could happen during thermal cycling, but it's less likely. Now another part of the equation may be that conformal coating has a part to play. So it's not good practice, not ideal practice, to completely encapsulate and underfill a package unless you know that the conformal coating expands and contracts at exactly the same rates as the package, the balls, and the substrate. And then that's what an underfill is. But a conformal coating material isn't necessarily exactly the same in terms of expansion coefficient. So you need to know that as well. But if you're going to conformally coat a board, it's perfectly reasonable to conformally coat the whole board, but not necessarily conformally coat underneath the BGAs. And some companies do that as part of their practice. So they try and eliminate that as a possibility. But if you know the material, it's got the same expansion coefficient, then it's less likely to be an issue. Now, thermal expansion and contraction is less likely, I believe, in this particular situation, because these seem to me, from an optical photograph that I've been provided, as cracks generated mechanically. So I don't necessarily think they're a thermal failure. Now, as a comparison, I picked a couple of examples out of my library, and these are failures which have been demonstrated with X-ray. First of all, traditional X-ray, then an X-ray with the funny colors added to differentiate the tracks and the laminate, etc. But it clearly shows the same sort of separation. But these were thermal cycle. This was a device which was thermal cycling because of the heat generated by the actual device operating, and in time it was literally wearing out. And this was right on the corner balls, where on a package you tend to find the corner balls are perhaps more susceptible than any other to mechanical strain. So there's a couple of examples. I still kind of think it's vibration or drop testing which the customer has a particular problem at this moment in time. So just before we move on to our next example, what I'd like to do is have one of our surveys. So all you need to do is select which one of these components gives you the most problems in the manufacturing process. So the one that gives you the most problems in the manufacturing process. So we've got over 100 people online. So please, if you just click the one that you feel gives you more problems than anything else. I'm just going to leave this for about 20 seconds to give everybody good opportunity to just click the one that they think. And as I said, I'll provide the results after the webinar. Okay, we're up to 70%. 70% of the online delegates have participated. So just give it a couple of more. Okay, that's 90% of people that participated. That's great. Okay, we'll stop there. So that's our first survey. And just if you joined late, the idea is we're just having a couple of surveys on different aspects of electronic manufacturing, just to get a feel for where we are, who we are, and how we're solving problems, hopefully, for people. Okay, moving on to defect number 3. Again, this was sent to me. This is a company producing boards for customers, and the customer wasn't happy with the contamination on the surface of this nickel gold board on the tooling holes. Now, this is, in my opinion, not really a defect. It's a cosmetic defect, a process indicator, if you like, but provided it's not going to affect the functionality of the product, provided it's not going to allow the board to sit correctly into whatever module, or it's not going to affect putting a screw or nut or a bolt or a fixing in this hole, then really it's cosmetic. And yes, the contractor should do something to improve the process which has allowed this to happen. Now, the most common reason for this type of phenomena is a wash-off, a poorly printed board which is then washed off and then reused, so reprinted with solder paste and then placed and reflowed in the normal way. That's the sort of most common. There may be others, but that's the most common. I personally believe that if you set up your printer and you use test boards and use the same test board all the time with a plastic sheet, you should never print a bad board again. You might print a bad board 10 or 20 boards later, but at least your first one will be perfect because you've done a test print. I personally don't like the idea of people throwing boards away because they printed it once and it wasn't very good. And in certain industries that happens, and some of you will obviously know which industries that is. Okay, so the most common reason is solder paste contamination. So I've just again gone to my library and picked up some examples. So the first one, top, is solder paste or solder particles which are trapped between the pad and the resist, so in the resist window. And the second example on the bottom is solder paste which is in the through hole or the fixturing hole, and the actual volume of paste in the hole or around the hole, around the resist and the pad on the top image, is way more than would be required to give the contamination you see in the photograph. It's surprising how far 1 or 2 balls of paste actually spread out on a gold pad. It is quite surprising. If you ever try this, you probably won't want to, but if you ever try it, it is surprising. So that would be my suggestion, is the most common reason for that. And if I was talking directly to the customer of the contractor in this particular situation, I would say 2 things. 1, accept the product as long as it's going to not affect the functionality and mounting. However, I would insist that the contractor do something about his controls in his process, and also perhaps learn how to clean boards off correctly and properly to eliminate paste residues being left on the surface. So I do sort of 2 things I would suggest in this particular case. Okay, defect 4. Now, these are connectors or examples of connectors that are mounted to boards, and this example was sent to me. And the problem here is that during the soldering operation, the solder paste is wicking up the pins and away from the pad area. And apparently this is this particular connector is featured on 2 or 3 products, and it happens on each of them. And the company concerned has done a number of experiments to try and reduce this particular problem. Now, the first thing I would say that obviously this is a specialist connector. This is not a standard connector. And ideally, we should, or the pins ideally should be parallel to the surface of the pad. And in that particular case, you are less likely to draw the solder up the pin and away from the joint area, reducing the volume that is actually there. That's the sort of first thing. Next thing, if you've got gold-plated pins, I imagine they're a very thin gold, less than a micron over nickel or another barrier layer. they'll be very solderable, very wettable. So solder does tend to migrate. Solder does tend to wet these surfaces and pull away. So what we've got to try and do is figure out what we can do to A, get the joint to make it acceptable, B, make it reliable. So whatever we can do in our process. So there's a few things that we can do. I understand that the company is using convection reflow. They're not using nitrogen, because if they were using nitrogen, I would have suggested reducing the nitrogen level. So having a much higher oxygen content. The company concerned uses nickel gold boards. They're using a water-soluble flux. So they've got great solderability. They shouldn't really have a problem with a soldering operation. So nitrogen is a nice to have if they were using it, but they're not. So certainly you could look at a solder paste which has got less activity, and that would reduce the amount of solder wick away. But what I would try and do is find a way of balancing the heat in to the part. So, and the ways you can do that is look at a profile. If you look at most profiles on reflow soldering systems, if you look along the sort of 6 or 8 or 10 zones, it's 120, 150, 180, 240, 260. And those temperature set points are mirrored. So below, for the bottom heaters, they're the same. But they don't have to be. So what I tend to do in a situation where I've got a high mass component sometimes, or I've got a intrusive reflow design, or in this situation where I'm getting wicking, I tend to put some heat, more heat in from the bottom. Now, remember that convection oven is basically a lot of blowers, but remember where the convection comes from. It comes from a solid slab, or it comes from a panel which is emitting hot air to the system. But that panel, that heater, can radiate heat. I know nobody wants to talk about radiation, but it's a mass. So if we say, for argument's sake, you've got air prior to reflow, just prior to reflow, the temperature is 240. On top side heaters. What about the bottom side? Flipping it and make that 260 at the bottom. So you're actually getting a little bit more energy, and you've got to experiment, because I don't know exactly the oven, the distance, separation distance between heaters, but all you're doing is getting a little bit more energy by radiation into the board assembly. So the solder paste is going to start to reflow based on the board temperature rather than the connector and pin temperature. So by doing that, you may well just get enough to reduce the solder paste running away onto the pin. Another thing that you should do that the customer has already tried is modifying stencil apertures, putting a larger volume of paste. And certainly that's the first thing I would have done in this situation. I would have looked at increasing the paste onto the solder mask. So bringing it perhaps as far as the end of the track just prior to going into the via holes. So I would extend it there. If the pitch, I'm not sure of the pitch, I would have also extended it out as well. So you're getting greater volume of paste to fill up the gap and give you perhaps a more robust termination. So those are some of the things I would have done in this particular situation for trials on this particular part. And just to illustrate this point, this is just one video clip. I did some work quite a few years ago with high-speed video photography, but this particular example is from a Japanese engineer who was using different techniques to look at wicking on solderable finishes and on solder terminations on components. And basically, he was able to demonstrate and set up so you could see the wicking effect that was going on. And in this situation, you can actually see the connector is getting up to temperature and drawing the solder away. And you get the same sort of thing take place if you've got poor wettability or poor solderability of the pad. Now, that's not the case in this particular example, the nickel gold boards the customer is using, I don't believe, but it's just trying to get the solder paste to reflow and wet the pad before the connector and connector pins start to wet. So it's just trying to control the time of wetting on the parts. And just another couple of examples of mine from my library. The one on the left-hand side is a classic example of poor wettability, poor solderability on a pad, and you can see all the solder paste volume has wet up the pin, which is, effectively what the customer on his process defect is illustrating. And on the right-hand side, you can see exactly the same with J-lead terminations on a board. This is actually a photograph from Texas Instruments when I was doing the training courses for them in Bedford, where we used to have a surface mount facility where we every month do a how to do surface mount training course, which was great fun. Okay, process defect number 5. But before we go on to that, what I would like to do is just give another survey. So the next survey is, what is your most common bare board problem? What is your most common bare board problem? So again, same thing. All you need to do is select which one of these you feel gives you the most problems in manufacture. So solder finish, solder mask, cosmetic, delamination, via through-hole failure. Okay, so as I said, we've got around 100 people on the webinar this afternoon. All you need to do is just select which one gives you the most problems in manufacture. We're up to 50%, we're up to 60% now, so keep coming, just tap which one you think in your own facility gives you more problems than other. I haven't obviously covered all the topics because of the limitations of the software you were using, but hopefully it will give you a flavor for what other people are suffering from. Okay, so we're up to 80%. Just give it a couple of more seconds. So if you just like to select which one you feel gives you the most problems in manufacture. So it's bare board issues in this particular case. Okay, that's over 90%. That's fabulous. Thank you very much. As I said, there's just 3 more to go. So I'm doing some work. I've got to get you guys to do some work as well. So process defect number 5. Now, a company was wave soldering products and products with BGAs on. And this particular example is a nice microsection which was done to illustrate the problem that they were facing. Now, if you were to look at this first of all and knew this was a microsection of a BGA, you would have thought that the solder between the BGA package and the board was actually a ball, but it isn't. What's actually happened here is the solder has gone up the via, wetted it, and gone up and formed a ball, possibly not a short, on the underside of the BGA, so sandwiched between the BGA and the PCB. It's a nice image. It's a nice image. I didn't do this microsection, I have to add. Now, what has happened here is, first of all, it is, in my opinion, and I think most designers, bad practice to have open vias directly underneath BGAs. That's the sort of the first thing. But what's actually happened here, this is, I think, if I remember correctly, this is a 0.3 via, but the company concerned had managed to get solder to penetrate up to the top side. But the wave solder machine they were using has a very aggressive, or had a very aggressive chip nozzle. And by virtue of the design being possibly, we might say, a little bit questionable, the process has allowed this to take place. So I think it's a good illustrator of what is bad practice. Secondly, in this day and age where we're looking at smaller and smaller pitches, finer and finer pitches, making sure that anything can't get from one side of the board to the other is good practice. And we do see quite a lot of examples during testing for fluxes and materials for selective soldering and wave soldering, where any residue left on the printed circuit board can end up as a contaminant and possibly lead to corrosion. So we want to try and minimize what we're introducing to the board. So certainly putting a big lump of solder underneath is not good practice. So look at vias, look at least plugging them with a solder mask, or plugging them in another way with the recommendation of your PCB manufacturer as a process, but don't leave larger, may I say, via holes open if you're going to be doing wave. If you're doing selective, then theoretically you shouldn't be soldering this particular point of the printed circuit board in the first place. So it shouldn't really be an issue for selective, but maybe well for wave soldering. Okay, so that's defect number 5, and I've just covered this with some text, which obviously you can read at your leisure. So Process Defect 6. Now, a couple of years back, I wrote a guide on POP, package-on-package assembly, and still some mobile phones use package-on-package products, and either first generation or second generation. And if you're not familiar with what a POP is, a package-on-package, if you imagine a BGA soldered on top of a BGA, that's kind of general description of what it is. So you've got a microprocessor and a memory device soldered together, which is mounted on a board, and we're soldering it all in one operation. But this is an example of underfill and exposed balls. So what you're looking at here is 2 balls which are not completely underfilled. They're exposed. They're visible. Now, the problem here is that we haven't put enough underfill onto the package, so when it's capillarying underneath, you've filled the gap, but it's pulling underneath, and there isn't enough to actually cover all the way around the package. I've done some trials on these with drop testing, and provided you've got a fairly large percentage coverage both on the bottom and on the top, you still get a benefit. So where you might have 1 or 2 balls exposed like this, I have not necessarily seen any issues. Not you get 50% failures because you've got a few balls not covered. There's not really any standards for this. I produced some guidelines which are in my POP assembly guide, which is available free to download. So yes, you would correct the process. You would look at increasing the amount of underfill you're adding, to get complete coverage. But personally, I wouldn't reject this. And I wouldn't go back and then underfill it again. I just correct the process which was causing the problem, which is what us as engineers really strive to do. So that's sort of process defect number 6. Process defect number 7. This is a PCB related issue. Now, when you do a microsection of a PCB, when you've got failures of a PCB, you normally do a microsection through the hole of the hole. So you go from the top of the board to the bottom of the board, and you actually see the hole of the hole, or the sides of the hole. Now, when you're looking at separation of inner layers, or you're concerned about there is a plating problem which is giving intermittent connection, I also do a vertical microsection. So imagine I'm sectioning through the board down through the hole until I get to the inner layers, get to a ground plane or a signal plane, and I'm looking for the connection of the pad to the plating through the hole. And that's what we're looking at. So the gap we're looking at, the black line there, is separation, complete and utter separation between the bulk of the copper and the copper in the plated through hole. And then the silvery grey area is the solder, and then the goldy coppery area and the next bit in, for want of a different description, possibly if I point it out, it might be easier. That's brass. So you've got copper, barrier layer over brass, and there probably was tin on there originally. That's the component termination. This is the bulk of the solder, and over here we have the plating and complete separation. So that board was a problem, in my opinion, to start off with. It wasn't necessarily something that was created in manufacture, assembly, or environmental testing. It was really originally a fault. and it's probably likely that that's resin smear on the board as part of the fabrication process. Probably. That's probably what it's likely to be. And if you were to follow the microsection round and look at the rest of it, if it's complete separation, then clearly that probably is the issue. So I would look at the board manufacturer. It's not an assembly fault. It would be very difficult for the assembly engineer to overheat it to this extent to cause this degree of separation. If it was sort of just a few areas of separation, I could believe it. But to this degree, no, I don't believe that. Okay, we've done 2 surveys. We're going on to survey number 3. And this is which process in assembly gives you the most problems or headaches, the most defects. So which process contributes most to defects? So again, as I said, we got around 100 people on the webinar. So if you just like to select which process gives you the most problems, the most headaches in manufacture, then just select that. And we'll just make sure we're over at least 90% of engineers on the call this afternoon to vote. So we've got a meaningful answer. So when I send you the results, you got some data that said, well, to your boss, that there was a lot of people on there and they all had the same problem as we have. It's useful. Okay, so just a few more to go. We're over 80%, just a few more to go. Excellent, excellent. Okay, yep, okay, that's great. We're over 90%, so that's pretty good, pretty good. So just a reminder, if you've never attended any of my webinars, I do them all the time. I do them at least once a month, or do them for other companies. I have an archive of different topics which you can find on my website. So there's an archive of previously recorded webinars. They're available. And I do, as I've said, webinars on demand for companies. So you can plan this into a training program you might have for some of your staff. And we can run webinars, once a month, once every couple of months, just literally to be Bob Willis on your training team. That's if you want Bob Willis on your training team. You might not, but at least there's 3 or 4 different options for you, which may be useful in your process, or possibly with your contractors, your customers, your suppliers. That might be beneficial to them. Okay, process defect number 8. Now, in a previous slide, I mentioned that I wrote a book on package, POP assembly. And I wanted to illustrate that with reflow soldering, with POP assembly, we can get open circuits, and in a similar way that you might have experienced with area array packages, where people talk about head-on pillow, head-in pillow. Now, with the second generation of POP packages, the bottom package has balls on the bottom, which solder to the PCB, and inside the plastic body of the part, you also have a solder ball. And the solder ball there is to join up with the package you put on from the top. So you've got a ball on top of a ball, and either by putting flux or solder paste on the top POP package prior to placement onto the bottom package, there's the way in which they join together. But one of the problems that we focus on, or have focused on in the past, is warpage and open circuit connections, which is one of the, the end result is the issue that we talk about with head in or on pillow. So if you look at the example on the left-hand side, I've ring fenced, or I've put a circle round. First of all, the blue are the small balls on the bottom of the package, which is soldered to the board. And the one that's circled in yellow on the left-hand side is more like a column. It's 2 balls which have become liquid, and you get a shape which is more like a column. and they've soldered beautifully. But if you look on the right-hand side image where I've circled it, you can actually see a ball which is sitting on top of a ball. And it's fairly easy with this X-ray image to see the differentiation between the bottom and the top ball. But if you look at the rest of the rows, the two rows there, you can see you've got effectively column joints. So we've got one open circuit intermittent joint. The balls haven't soldered together, which may be process related, flux dipping process, dipping into solder paste, dip paste that we use, or a warpage problem, which has contributed to that particular problem. So you've got to investigate 2 or 3 areas, but I would suggest it's probably warpage related. So if you know the history of the component, how much warpage you get during reflow, you'll be able to overcome that. But if you've got a problem, and let's say, for argument's sake, you were using a dip flux for this process, I would investigate using a dip paste. I prefer dip paste because it overcomes issues of open interconnections, because you're putting something which is a solder adding to the joint. If you just got 2 balls, and if there is any small gap between those 2 balls, the flux won't aid the connection, because you're not adding any more volume of solder to those 2 connections. You're just adding flux, which is providing the opportunity to solder, but not actually giving you any more volume of solder, whereas dip paste adds solder volume to the potential connection. Okay, moving on to process defect 9. Now, this is kind of a question that was asked to me about modifying data. So if you're a contract manufacturer, you will have come to an agreement with your customer, and you will receive a package of information, design files, process files, placement files, all the data on the components you've got to source and use. I personally believe that where there is a clear problem, a clear issue, then yes, you should be able to modify the data. And the data we're talking about in this particular case was the placement data files. Now, I've just illustrated here from my library just examples of slightly misplaced QFP at the top, 2 components where we put the components in the wrong place, which are clearly obvious, and slight misplacement of the ball, a BGA, onto paste. Okay, so they're just placement errors effectively. But the point is, have this is it right to modify data? And if I just take a couple of examples, first of all, if you've got a placement file which the coordinates or the center location coordinates or any coordinates are not correct, then inevitably you are going to correct them. But if it's modifying data that's been given to you, then yes, you should inform the customer there's an error and try and get to the root cause why it's an error and fix the root cause so it doesn't happen again. But modifying placement data to make sure the parts are where you want them on the pads, I think is fundamental. The problem does come if you continually make changes, then the data is a very bad representation of the original data you've got. And I know some companies don't like to change data for this very reason. But I don't want to use data which isn't allowing me to give the customer what he really wants, is a good product. So again, communicate that, discuss that. If you're going to change anything, speak to the customer first of all and get acceptance on email so that you've got traceability. But if we just take another example, if I may, a classic example is stencil file data. Now, there are contractors who will get a stencil file data from their customer and completely change it, which if it's giving the customer a good quality product, I've got no problem with at all. But tell the customer what you're doing. There is quite a lot of data which comes out from CAD systems which is not right. And I have worked for customers where they had followed what they were told to do, but clearly the information or the sort of data wasn't any good. So what do? Use bad data or use your own engineering expertise to modify the stencil data and give the customer what he really wants, a good product. So keep people in the loop, but please use your own expertise. Normally speaking, you'll probably find your stencil manufacturer modifies the data to start off with, and that's not uncommon practice. But please check your check plots. A lot of companies, they get check plots back from the stencil manufacturer and just say, yeah, that's okay. I'm not diminishing the problem. I'm just saying that we don't check it ourselves. So yes, I think the data can be changed, inform the customer, then there's no comeback, but you are ultimately trying to do the best job you possibly can. So I would say, yes, you can change data. If I may, just go on to one other point. I have a lot of issues sometimes with customers not allowing modifications to a design. And the classic one is hole to lead ratio. For intrusive reflow, selective soldering, wave soldering, solder shorts, all these sort of, and just by getting the hole to lead ratio right, rather than following what the connector manufacturer said on their data sheet, which 9 times out of 10 is not right, that can improve yield, improve functionality and reliability. So again, you can't change the data to produce the board without permission from the customer, but customers, please be open to the change, because all the contractor manufacturers trying to do is make the best product at the most economical price and the most reliable product for you. So again, listen to the conversation, please. Okay, one final survey before we move on to another group of questions, and this one is on what do you specify or what do you ask for when you're specifying PCBs to IPC. So when you use IPC, what do you actually ask for? Is it level 1, level 2, level 3? We don't specify the board at all. So which one most represents you and your product? So we're over 70%. So just a few more clicks, everybody that's online. And for those of you who just joined us recently, we're around about 100 people on the webinar. And we're just doing a couple of surveys just to give you a feel for who's on the webinar this afternoon and what problems they see or problems they have had in manufacturing, trying to put give you a little bit more of an understanding on the inspection criteria used or specified when building boards. Right, we're over the 90%, so we'll close that survey. So that's all of our surveys done. So let's carry on. So process defect 10. Now this is kind of similar, I guess, to the problem that one of our other delegates highlighted, which is the cracking of tracks leading into BGA terminations. But this is cracking of a track or a copper track in a flexible circuit. So the flexible circuit's mounted to a rigidizer strip, a rigidizer circuit, part of the original board possibly, but you've got this cracking. Now, flexible circuits are designed to flex continuously for hundreds of thousands of flexes, or they're just designed to flex to put into a product. So again, you have to design the flexible in a way which gives you what you want. So if it's a case you're going to flex it once, or possibly 2 or 3 times, no more than that, just literally to be able to assemble it into the product, and that's the end of it, you probably have a different approach as opposed to a flexible that's going to take hundreds of thousands of flexes. So that's the first thing. But on this example, you're flexing directly against either the bare board or the rigidizer strip, and that's where the crack has occurred. So the polyamide tape on both sides, that's the sort of browny grey area, sandwiching where the copper is cracked is flexing, and over time is causing that to crack. So this is really a design issue. So you should really look at some of the excellent design rules that are out there, and also from my good friend Joe Feldstad, his Flexible Circuit Technology book. I think it's in his 4th edition. I think the 5th edition is due to come out soon because I wrote a chapter for it on assembly. But that is an exceptional book, and the nice thing about it, it's free of charge. Everybody's giving books away free. It's wonderful. But no, Joseph is an excellent engineer, and there's a lot of very useful data in there. So again, if you're interested in flex failures, etc., and how to design a flex, but of course, talk to your PCB manufacturer. If they make flexibles, they obviously know a lot about flexibles. So again, with any design engineer, understand how a flexible is made, or a bare board is made, or components are made. If you're designing a component into a product, the more you understand about a product, the better you can design for the use of that particular product. So that's process defect number 10. Process defect number 11. And this sort of goes back to the point I was raising earlier about knowing your product, but also hole to lead ratio. It is so important. If you have a hole to lead ratio where the hole is very big and the pin is very small, and it's a single-sided board, which it is in this particular case, you'll get crack joints quite quickly. And it depends how much strain is put on the board, the solder joint, and the pins on the connector, or whatever it might be. But these cracks are in a single-sided board joint. Now, if you go to a plated through hole board as opposed to a single-sided, there is obviously quite a significant jump in the price of that board. But equally, what you could look at is using eyelets and griplets. Now, this is very old technology, but it works. So having an automatic eyelet machine and inserting eyelets to make 5 or 6 holes in a printed circuit board, which has got heavy components on, is not as significant a cost when you look at amortizing it over a long run of products. Or alternatively, if it's a small run of products, then you could easily do this yourself. It's not difficult to do. And putting an eyelet in, is what it's doing is just giving more strength and rigidity to the solder joint, and the eyelet is just creating a plated through hole effectively. But again, it works quite nicely. And you used to see this a lot in VCR, TV manufacturers, and still see in TV manufacturers used today. So just as to put a little bit more of a story behind this, if you look at this, this is a cross section. So the break in the solder joint, as you can see, is directly in this particular plane, directly over the edge of the plated through hole, or the single-sided board, the pad on the single-sided board. If you had decreased the plated, I keep saying plated through hole. If you decrease the hole size, so made the hole to lead ratio much smaller, the actual volume of solder on that joint would increase. So you'd get a concave meniscus on the outside that you can visibly see, but also you tend to get a concave meniscus on the pin. So the cross-sectional area of the solder joint would be greater by doing that simple design change of the hole to lead ratio. It wouldn't stop a failure, it would prolong the life of the product. So if your product's designed for 5 years, you might get 8 years out of it. That's just an example. I can't put my hand on my heart and say that, but just an example. So again, that hole to lead ratio, the volume of solder and the shape of the joint is important. But if you need longer longevity, or you've got very heavy components which are subject to drop, shock, vibration, then eyelets might be an option for you. You can obviously go to plated through hole boards, but that will have quite a significant impact on the cost of the printed circuit board for your process. Okay, so that's a few defects that I've gone through. I've hopefully solved a few issues for those delegates that have joined us and been kind enough to send in your questions and comments to me. Hopefully I've addressed all the ones that have been sent in to me in advance of this particular webinar. And just a reminder, that's what I do for a living. I run events like this. I hopefully solve problems, but it's just nice to do it as a member of a team. So if I can do that as part of your team, that'd be really, really good. So I'm now going to move into any other questions. So if there's any other process questions, I noticed that we've got at least 2 or 3 which have been sent in. So again, I'll pick up on those. But if you've got any other questions, just drop the question onto the control panel, type it directly in there, and I'll do my best to answer them for you. And just a reminder that these are a listing of all of the monthly webinars we've got coming up. So we had tombstoning of components today at 2:30. Sorry you missed that. And we've got manual cleaning of printed circuit boards, pin and hole intrusive reflow in the next 2 months, and all of the others is my program for the rest of the year. And dates will come out every couple of months. A reminder, that's one thing that's available to you. Our video archives available to you, the recordings, and also our webinar on demand. So if you've got a topic you want to train your staff on or your operators on, then perhaps I can arrange something specifically for you. So back to any questions. Let's have a look. Okay. Right. There's one person missed the first defect. I'll have to explain to it offline rather than go through it all again. Somebody asking about defect 9 is manufacturing abuse. If you'll bear with me, I'll have to go back. Defect 9 is manufacturing abuse. I don't quite get that, but so Amber, I apologize, I don't quite get that comment. But anyway, let's move on. Is this webinar will be posted on your website? Yes, the recording of the webinar will be sent to you as well as the slides, and it'll be on my YouTube channel. Next question, was the real cause for the solder crack in the plated through last? What was the real cause for the solder crack? Yeah, okay. Well, basically, it's fatigue. That particular solder joint was used in an application where it wasn't appropriate. The component was, force was being applied to the component as part of the operation of the equipment, and that led to that. That's why I said that you could have made the hole smaller, got a bigger, more substantial joint, and it would last longer. It wouldn't overcome the problem because mechanically it would fail at some point. So yes, it would have improved it. You would have got a longer life expectancy out of it. It wouldn't really have overcome the problem. But single-sided boards and hole to lead ratio is crucial in getting it right to get the best possibility. Next one, how to reduce voiding with thermal parts. Well, you know, voiding, I mentioned, if I just could sort of briefly run through that. First of all, obviously paste and profile. Those are sort of 2 key things. You've got to experiment and get the best paste combination and profile to get the best results. Next thing, look at stencils. You know, get your design right. Do not get solder going into vires because that inevitably will give you more voids. That's inevitable. But also look at the other things I listed. Outgassing from the plating on the parts. Some parts outgas. Outgassing from the surface of the plating on the PCB, from vires, from around solder masks. These are all things I've investigated and demonstrated by virtue of me showing videos that they potentially can be root causes. Right. Question here, what should be improve with regard to reflow? Well, you've got to experiment. When you've created volatile material, which are gases, either from volatiles within the flux or the actual soldering operation, as you wet a surface, you're generating a chemical reaction. So they can be byproducts of that gas. So either one of those, how you experiment with different profiles is important. Another experiment that I've done in the past is taking boards, printing paste, and using a glass slide. So putting a glass slide and changing the profile with a profile simulator. So basically a reflow oven with a glass window and a camera on, and seeing how the profile affects the amount of volatility. These are sort of the experiments you have to do, other than put thousands of boards through your process. If you can see what's happening, you can probably improve something to see if that's going to work in practice. That's why many Japanese companies have created video simulators, sell them on the marketplace, and use them in MPI, and also for proving new designs and new component designs. Okay. Right. I'm just reading through the question. It's right. With a lot of defects that we have today, where you can't actually see a product, the different techniques you can use obviously is X-ray. And I use X-ray. I can use X-ray to look at voids. I can look at X-ray to look at dendrite formation, corrosion underneath packages. So there's, X-ray is a great tool. You can use SAM, so acoustic microscopy, to look at separation of different layers of components, packages, etc. So that's another technique. The question basically was, what techniques are non-destructive that you can use? So those are sort of two techniques, but wherever you can, try and simulate the problem, and then you can see it, and then you can move on. Unfortunately, at some point, you may need to cut a board up. You might need to do a microsection. And the reason for that quite often is that if you're taking the liability of those failures or the consequential loss of finance on those problems, then you need to go to the baseline, which is doing the microsections. But as components and failures get smaller and smaller and smaller, using traditional microsectioning techniques is difficult, because with very, very small joints and surfaces, you create more damage sometimes with microsectioning. So classic example is I was working on a problem with ultra small via holes, capped via holes, and I could do the microsections and show the end result, which is good, but the customer wanted more proof. So we went from a microsection which may cost you £400 to another technique which costs around £5,000. But if you need the data, if you have to have the data to prove the point from a scientific point of view, then it does become a lot more expensive. Okay, next question: is it correct that with N2 nitrogen atmosphere, voids are harder to escape due to higher surface tension? I personally don't believe that. I don't believe that. If you take a product which is running in air and then a product which is running in nitrogen for the same solder paste, you will see differences, but I don't necessarily believe it's because of the surface tension and the escape of the gases. But again, one of the things you can do is do a process simulation with solder on a board with a glass slide and watch what happens. And there's a couple of paste manufacturers. I know that Kester did some work using this technique, which I use, and there's been a couple of others. So again, use a technique which allows you to understand and see this actually happening. Okay, so we've had 60 minutes and another 10 minutes for some extra questions. Hopefully, let's just go to the end of the slides. So hopefully that's been of some interest to you, some value to you. I'll put the results out of the survey after I've sent out the slides, so that'll probably be tomorrow now. But thank you very much for attending. Hope you found this interesting. Hopefully you found this might be something that might be useful to you and your team in the future. So if you have a problem, rather than wait for weeks while you're trying to figure it out, then there might be a benefit of having somebody else involved on your team. Obviously, the quickest and simplest option is getting a supplier involved, but sometimes an independent view might be beneficial to you. So once again, thank you very much for attending. Hope you've enjoyed it. Please attend one of our webinars in the not too distant future, and you have a great afternoon. Thank you, and good afternoon to you all.